start out electrically neutral, meaning they have an equal number of positive and negative charges. When you rub the balloon against the sweater, electrons are transferred from the sweater to the balloon due to the friction. This movement of electrons causes the sweater to lose some of its negative charges, leaving it with a positive net charge. At the same time, the balloon gains those electrons and ends up with a negative net charge. This process illustrates how mechanical work, like rubbing, can create static electricity by redistributing charges between objects. The terms positive and negative charges are what we use to describe the two types of electric charge. These concepts were first suggested by Benjamin Franklin, and they help us understand how electricity works. Franklin's image appears on the $100 bill. If you start with zero money in a bank account and then withdraw $100, your account balance will show a debit of negative $100. This means the account is overdrawn or in debt by that amount. The plus and minus signs indicate whether money is being added or taken out, so withdrawing $100 leaves you with a negative balance of $100. This example helps show how positive and negative values work in financial transactions. Franklin adopted these ideas to explain static electricity. Here, we see a comparison between a bank account and electrical charge inspired by Benjamin Franklin's approach. Just like a bank account can have a zero balance, surplus funds, or debt, electrical charge can be neutral, positive, or negative. A neutral charge means there is no net charge, similar to having zero in a bank account. Depositing funds into a bank is like adding positive charge, putting in an electrical surplus. Conversely, withdrawing funds is like taking away charge, resulting in a negative charge or deficit. Franklin's way of labeling these signs set the foundation for how we represent positive and negative charges today. It's a common misconception that making an object positively charged means adding protons to it. In reality, protons are locked tightly inside the nucleus by the strong nuclear force, so you can't simply add or remove them. Instead, when an object becomes positively charged, it happens because electrons are withdrawn. Electrons carry a negative charge, so pulling some away leaves the object with a net positive charge. This is the true atomic basis behind positive charge, rather than altering the number of protons. The law of conservation of charge tells us that the total charge in a closed system always remains the same. It doesn't get created or destroyed, it just moves around. For example, here we have two spheres, each initially with no charge, so the total charge is zero. When we transfer 5 electrons from one sphere to the other, one becomes negatively charged while the other becomes positively charged by the same amount. Despite this shift, the total system charge remains zero, showing that the net charge is constant. This principle works just like the total momentum in a system. It's conserved, even as components within the system interact and exchange charge. Charge is one of the key properties of matter that determines how particles interact through electromagnetic forces. This charge comes in fixed amounts, meaning it exists in specific, indivisible packets rather than a continuous range. This idea is known as quantization, and the smallest unit of electric charge is called the elementary charge. Its value is incredibly tiny, about 1.60 times 10 to the minus 19 coulombs, with the coulomb being the standard unit used to measure electric charge. Understanding this smallest unit helps us see how electricity operates at its most basic level. Did you know that you can charge an object without touching it? This is called charging by induction. The blue rectangle on the left represents a negatively charged rod, while the circle on the right is a neutral conductor. When the negatively charged rod comes close, it repels the electrons within the conductor, pushing them to the far side, shown here in blue. Meanwhile, the side closer to the rod is left positively charged, shown in red, because it has a deficiency of electrons. This separation of charges inside the conductor is called charging by induction, and it causes the conductor to have distinct positive and negative regions without any direct contact. If the conductor is connected to the ground where it is negatively charged, the excess negative charges to flow away. Once this connection is removed and the external charged object is taken away, the conductor remains positively charged. This setup helps us understand the principle of charging by induction without direct contact. This image shows that the sphere became positively charged by losing electrons, even though it never came into direct contact with the charged rod. Particles with the same type of charge, like both being positive or both negative, push away from each other. This is called repulsion. On the other hand, when particles have opposite charges, one positive and one negative, they pull toward each other. This force is called attraction. These basic rules explain a lot about how electricity and magnetism work in everyday life. To move forward with calculating forces, we first need to measure the exact amount of charge involved. This is done using a coulomb meter, which shows the total accumulated charge directly on its display in units like coulombs or microcoulombs. The meter ensures we have a precise reading of the charge that has been transferred by friction or induction to the object, allowing us to work with accurate values for any further analysis. Let's review Coulomb's law by breaking down its components. The force between two charged objects is directly proportional to the product of the magnitudes of their charges. These are represented here as Q1 and Q2, measured in coulombs. This force is also inversely proportional to the square of the distance between the charges, indicated by r squared, meaning as the charges get farther apart, the force decreases rapidly. The constant K is Coulomb's constant, which helps us calculate the force in newtons. This constant has a specific value that keeps the units consistent, ensuring the force is measured correctly. Together, these parts give us the electrostatic force between 2 point charges, helping us understand how charged particles interact. Now that we have visualized the setup with two charges and their distance, we can clearly define the variables we'll use. The first charge is positive 2 microcoulombs, converted to 2.0 times 10 to the negative 6 coulombs. And the second charge is negative 3 microcoulombs, or negative 3.0 times 10 to the negative 6 coulombs. The distance between them is 0.05 meters, and we'll use the Coulomb constant, which is approximately 8.99 times 10 to the 9th Newton-meter squared per Coulomb squared. Our goal here is to calculate the force between these charges and understand its direction. This gives us everything we need to apply Coulomb's law step by step. To wrap up, after visualizing the two charges and defining the necessary variables, we substitute the values into Coulomb's law formula. Using the absolute values of the charges for magnitude, we calculate the force by plugging in the constants and distance. Simplifying the numbers step by step gives us a force of about 21.6 newtons. Since one charge is positive and the other is negative, the force between them is attractive, meaning they pull towards each other. This concludes the calculation and explains both the magnitude and direction of the force.